Good afternoon. Thanks for coming. I'm Yanina Cochetti. I'm from Argentina, and I work in the Observatory of La Plata, in two different institutions, but in the same building. That is the Astrophysical Institute of La Plata, that depends on Cochetti and the university, and the Faculty of Astronomical and Geophysicist Sciences from the university. And I'm also a member of the POEMS project. That is why I'm here. Yeah, so I work mainly on peculiar stars, mainly focus on VE stars, and mainly focus in spectroscopy. So this is like a brief scheme of this presentation. I will start with the introduction. Probably there could be some people that doesn't know about VE stars, and especially why we are interested to analyze infrared data. I will go on the motivation that is based on some previous work that we are doing now. I will describe what we are doing now and with code, some of the results that we achieved, and my conclusions and what are our next steps. So VE stars, what are VE stars? There are early type stars that show or have shown in some moments hydrogen emission lines, especially H alpha. There are mainly B stars, that's why we call VE stars, but they can be also late O or early A stars. These emission lines are formed in a circumstellar envelope that surrounds the star, which are mostly compatible with a disk geometry in Keplerian rotation. So here is a schematic of a V star. This is the central star, and this is the disk that we are seeing like equator on. And we can see that depends on how we are looking at the star and the line that we are looking. Here, H alpha, H beta, and some iron line. The profile can present very different shapes. So we can see only one peak, or the peak is like separating. We are looking at an equatorial point of view. And we also can see this type of profile that we call shell profile. So what we want to observe in the infrared region? Well, in this region, this star presents moderate flux excess and a lot of hydrogen lines. These lines are forming a region that is closer to the star than the lines that we can observe in the optical part of the spectra, like H alpha or H beta. For example, this is a schematic. If we have the central star, we can see that there is one region for different lines that we are observing. So we can obtain different information depending on which line we are observing. The infrared lines, their photospheric absorption is almost negligible. So we are observing just the envelope, not the atmosphere. So the study of these lines is a great tool to obtain information about the innermost part of the disk, about physical structure and dynamical structure. So this region has started to be analyzed in the last decades, but most of the works focus on a single part of the infrared spectra, or just in one object, or just in one specific line. So there's not a lot of work done in a wider spectral range. That's why we started to do a few years ago. And there is a lack of synthetic spectra to compare our observational data with. So we are working on that. So what we have done, we observed 22 galactic VE stars simultaneously in the J, H, K, and L band in the infrared region. And well, there is a work that has been published last year that is like the infrared atlas with all our data. And we are working on characterize the envelopes based on this spectra that we publish. This is a work in progress. So this is what we have published. This is the paper that we sent last year. And here we can see part of our spectrum. This is the J band, H, K, and L band, and as you can see, there is a lot of lines. Here you can see all of these are the Humphrey series. We can also observe bracket alpha, and the end of the bracket zero, the normal is there. Some Paschen lines, some full lines. So there is a lot of information here. So the first thing we did was to classify our stars according to a criterion that was proposed by Meniken and collaborators.
Can I ask you, this population of the stars that you are using, so what is the largest distance?
There are closer, yeah, there are in Milky Way, yeah, there are galactic. Yeah.
No, Milky Way meaning
Close.
close meaning 1 kiloparsec from us?
I don't remember exactly, but they are so bright. Yeah. I'm not sure how many kiloparsec, but they are very close.
Just a few kiloparsecs.
A few kiloparsec.
Yeah, it's not very.
Not more.
A few can be 4 or can be 7. Depending on who
Okay,
is-
up to 2.
up
Most
to-
of them up to 2 kiloparsecs. In the galactic disk mainly. Not high latitudes.
Okay, thank you. Sorry for the interruption.
So we classified with this criteria. What this criteria said? Well, if you look up to the L band of the star, you can see Fun gamma and bracket alpha line, and also the Humphrey series. So if the Humphrey series lines are as intense as Fun gamma and bracket alpha, the star is classified as group 1. And if the Humphrey series is not as intense as these two lines, the star belongs to group 2. There is also a group 3 that are stars that doesn't show emission in these lines. So we classify the stars with this criteria, and what this person said it was that these groups are related with the optical depth of the envelope, because they put their stars in this diagram that was a previous diagram that is made by Lenore, that use the flux ratio of the lines, and here is the group 1 and the group 2 stars, and this region is closer to an optically thick approximation, and this region is closer to an optically thin approximation. So the position in these diagrams give us information about the optical depth of the envelope. So group 1 are optically thick, and group 1 are optically thin. So we classify our observation with this criteria. There was another previous work that was made by Yanina and collaborators, that with another sample of objects, they both classified as group 1 and group 2, and they find that group 1 stars follow this relation between the equivalent width of bracket alpha and the equivalent width of bracket gamma, and group 2 stars follow the other one. So what are we saying here? The red symbols are from our group 1 stars that are in the line that corresponds to group 1 object. The blue one are group 2 and follow the relation for group 2, but there are some green points that follow the relation for group 1, but if you see the L band spectra, they're more close to, the Humphrey lines are not as intense as Gamma and bracket alpha, but they are intense enough. So they are like in the middle of this classification. Yeah.
Can we interrupt?
Yeah.
So what is Bra-alpha? Branga?
Bracket alpha, the line, this one.
So this is due to what transition? So
Bracket is for level 4, so it's 5-4.
so it's all hydrogen lines.
Yeah, they are all hydrogen, yes. Yeah.
Everything is hydrogen, but it's called with this if we have Bra-poof.
Yeah, it's bracket series, Poon, Humphreys, and Passion.
Okay, thank you. I was a bit lost with the name.
Lyman, Balmer, Passion, Bracket, Fund.
Okay, I only know
So yeah, we also put our objects in this Lenorser's diagram that I showed you before. So this is our group 1, our group 2, and our middle group. And there's also a diagram that was was presented in this other work by Yanina that you can see with another lines that you can separate group 1 and group 2, and our group in the middle is in the middle. But both of these two diagrams and these lines and the Meniken criteria are based on L-band spectra. And we didn't have L-band spectra for our complete sample because we have some data that was taken in Las Campanas in Chile that a fire spectrograph doesn't observe L-band spectra. And we also have data for Gemini, and we observe J, H, and K band together with across dispersal mode, and L band in another observation. So there were some objects for which we only have JHK and not L band. So we try to classify both also these stars for which we didn't have L band data. So we couldn't use Meniken criteria. So I made these other diagrams that it's made in a very similar way of the Norse's diagram, but with lines that are not in the L band, but in the other ones. So we can put all our stars there. So we see that there is still a separation between the blue dots here, but the red and the green ones are like together. So we propose that they are actually should be the same. That there is actually part of the group 1. I mean, there is a gray area because the Humphrey lines are quite intense, but probably if you see the spectra, they are not as intense as the other lines, but they are intense enough. So we propose to that it's better to classify between groups, not by seeing the spectra, but to measure the lines and put some limit that is over there in these different line flux diagrams to separate between group 1 and group 2 stars.
How do you decide where to put these lines or demarcation lines?
We base mainly in these two. As we have already seen that it was a lot of similitudes between both groups, we say, well, this should be in the same group, this should be in the same group, and then we observe here where these objects are. So here you have almost all the only green and red. There is here a blue dot, but it's over this line, so it can be like moving from one group to another because these stars are also variable and the envelope is not stable, so it can be developing or it can be losing their disk. So it's possible that it's not exactly separating the same way in all the graphics because we are looking different parts of the disk with different lines, so it can be some mixing. But there is one here that, I mean, we put the line here, but it could be a little lower because this one is like in the middle here. So this one, we can't say it's group 1, group 2, because this line could be a little lower. The important part is to have this one on one side and the blue ones in the other side. Yeah. So we classified our data. We found 9 stars in group 1, all very hot, and 10 stars in group 2. That 7 have temperatures below 18,000 degrees. So this is in a good agreement with some previous work, because it is thought that early type VE stars can develop envelopes that are more dense, so they should be in the group 1. But as the envelope is in some moment loose, the envelope can pass through an optically thin state when it is losing. So in group 2, there could be both early and late type stars. So as a resume, we define new complementary criteria to mannequins, and some objects present optically thin and other present optically thick envelope. So once we have that, we started to work more deeply in the characterization of each envelope. So one thing that we made is these diagrams with line flux ratio, and the continuous line is the line flux ratio expected if the envelope is optically thin, so optically thick case. And this is the expected if the envelope is optically thin. So we see that the higher order members follow the optically thin relation, and the lower order members has to depart from the optically thin. But in which line this departure starts and the shape that these curves have, it's not always the same. So we think that this behavior could be related with the density structure of the disk. So we are trying to analyze this, and this is why we needed to have synthetic models to compare our models and our measures with different densities across the disk. So that is why we started to do it. There is a code that is HDUST that has been used mostly to model H alpha. There are some papers with bracket gamma, and there has been used also to model the spectral energy distribution, but it hasn't been used to model a lot of lines at the same time. So that's why we are doing that. So this code is a non-LTE Monte Carlo code that allows us to solve the triative transfer, triative equilibrium, and statistical equilibrium in 3D geometry. You can put different gas distribution, different gas density and velocity distribution, and it works with a 25 level atom for hydrogen. It's only for hydrogen, and which 12 are in non-LTB, like the first 12 level, and other 13 in local thermodynamical equilibrium. And this is the density that we are using. There's the central density and the base of the disk. There is a power law in the radial coordinates, and it's a Gaussian in the vertical coordinate. And this H follows this relation that is for disks that are vertically isothermic. So we needed to start with something. So we choose some central parameters, or some parameter from the central source, the central star, that are there. We start with tensor masses, 5.5 radius, this luminosity, and this rotational velocity. So this is around a V2 star. And we needed to choose also the density distribution. So we saw this diagram that has been published in this work, where they analyzed the spectral energy distribution also with data. And they found that the exponent, this m, is the same m that I have in the other expression. They found that this value, the exponent of the law, is related with the state of the disk. So higher values of the m is related with forming disk. In the middle, we have a steady state disk, and in the other part, we have the disks that are being loose. And there is also a forbidden zone. So we choose values from the.
Excuse me, I missed what is the n value? What it is? I missed. Sorry.
The m here is the n here is the exponent of the power law.
I don't think she sees the cursor.
Ah, yeah.
I do not see cursor. Yeah, not the laser. It is m, but n.
And here because
It is the same.
Yeah, because actually in the code you have to put an n value that it's not that n. So it's a mess. So this n is the m for the exponent law. That is the m that is in the table below. Yeah, I don't know. I think I'm gonna choose the same value for everything.
Okay, thank you.
So let's say on this way, we choose different value of the exponent and different values of the central density. But in the code, we don't put central density in mass density, but in numerical density. So there is also transformation channel up to 44, 24 in the middle. But well, we choose point across this area to model our disk with a V2 central star. So, HDUST give us a lot of files that needs to be processed and read with HDUST, that is a package from Python. And we also analyze the spectra that we'll read from them with another Python package that is spectroscopy that allow us to normalize and find the line parameters. And we use as a criterion for the convergence of this simulation if the temperature converges. There is some final plot that can make with this HDUST. There are different, like the last iteration from the code and an average. So we can see that in the last iterations, the temperature is like almost the same. So the code converges. And this is the shape that it should be like initial drop when we are going outside the disk, and then we started to increase the temperature again. There is a spectra just for show a spectra from these values, this exponent and this density at the base of the disk with an inclination of 0 degrees that is seen as polar. So we put together, comparing between different parameters, our line profiles. So this is from a value of 3.5 on the exponent of the power law, and for different densities. We see that there is an increase in the intensity of the line between bracket 12 and bracket alpha. For most of these lines, at least, the more intense lines are for the higher density, except for bracket alpha, when there is the higher is for like the middle densities. So we analyze this for our different models in different inclinations. This is 0, and this is for 30 and 60. And we also measure the parameters of the line. So here is the equivalent width over bracket 12. We choose bracket 12 because it's the last one that we could model properly, because it's the last level that we have in non-local thermodynamical equilibrium. So as the first plots that I show you that we are working on, we use as a reference bracket 20 actually, but we don't have bracket 20 yet. So we are using like the last line that we have. So we can see here also that the equivalent width is increasing between bracket 12 and bracket alpha, and the slopes of this increasing depends on the M value. We also measure the flux, and we see that the behavior is non-monotonic, that is like the behavior that we are seeing in our data. The flux increase up to bracket 10 and then start to decrease. And we also made this plot with the equivalent width between bracket alpha and bracket gamma, and the two relations that I told you before. This one, the continuous one is the one for the group 1, and the other one was for stars in group 2, just to see what happened with our theoretical spectra in this plot. And here we have also the equivalent width of bracket 12 and bracket 11 that follow like a line, but the position in this diagram is related with the exponent. The color is according to the exponent, and the size of the dots are related with the density. The smaller the dot, the smaller the density. So to try to test if this has any sense, we try to overplot with our real data. MX pupils is the star with the stellar parameters closer to the object that we model. So we overplot here in the little stars. There's the data. We don't have a observation from the L1, so we doesn't have bracket alpha. But we can see that, for each density, the exponent that fits better is the lower one. You can see that it's always in the lower part of these curves. But we cannot choose with this which of these three is like the correct one or the more probable one. And we also overplot the spectra. The red lines are the real spectra, and the other ones are the different models that can fit, the models that fit better in the other diagrams. This part is very noisy, but for these three that are the part more close to the star that bracket gamma, it looks like a more probable is this parameter of this envelope, the M3 and the central density 5, the 10 to 13. But there is a better fit for bracket gamma with another parameter. That can happen because, as I mentioned before, the disk is not stable. So it is possible that an innermost part, the sample part, the lines have already changed their density distribution, and the outer part of the disk doesn't know yet. So it can be possible that we need to continue with that, because also there can be some difference in the inclination that we are using, because we are using here 60 degrees, and the inclination of that is 50 something, that so it can be changed. And we also overplot another star that it's not as close in parameters that the other one, but just to know what happened. And we have here more difference between the models that we can fit. There is one that are more close to our data, and another curves that are not good at all. But if we see the spectra, there is some that fits quite well, but there are another that no, not at all. The orange is not for sure a correct option. So we saw that the increment of the intensity depends on the density of the base of the disk and to the exponent of this power law distribution, and that the line usually increases in intensity between bracket 12 and bracket alpha with a slope that depends on the density. We also see that our models are close to the expected to group 1 stars in these diagrams between equivalent width, with smaller equivalent width for larger M values, for larger exponents of the power law. And our simulation describes quite well our observations, but there is some degeneracy between different models that we cannot choose just one set of parameters to describe this. So what we want to do now? We want to include higher terms from the bracket series, because that will allow us to separate better these curves, because we can start this point should be that, I mean, this line will be different, so these curves are expected to be more separated, so probably we can fit better with that. And also we want to include other hydrogen series. We started with bracket because as we only have up to the 12 level, it was like the best option now, because, for example, in Humphrey lines, we are starting with Humphrey 13, so we cannot model properly with the actual hydrogen model the Humphrey lines that we are observing. And we want, of course, to add other spectral types, so we can start to try to overplot all our spectra with another spectral types, and trying to see if we can obtain some information about the density structure of our disk. So that's all. Thank you. You take any pictures? Because Michaela will ask me about.
If
For the poems.
Yeah. It's mandatory.
and people listening online can speak or write them to the chat, so we could see.
I have a question, this is very basic question, because, yeah, I was a bit lost with what you call peculiar star. So I keep asking this to myself. So let me see if I understand. So basically you have a normal star, meaning that the interior of the star is.
No,
The
it's called
same-
peculiar because they show emission lines, and there's a lot of another groups of the stars that also show emission lines because of the different
But my
envelopes.
I made wrong the question. So the peculiarity comes from the fact that this star is a normal star that just has a disk, and this peculiarity, these emissions comes from the disk, or is it the interior, the evolution of the star, which is fundamentally different to other stars?
No, it doesn't look to be more different than just a fast rotator star. But there is not have any difference between abundances, or not at least this one. There are some other peculiar stars that have.
But if I go to my basic course on stellar dynamics, and I take the simple equation, hydrodynamical equation, Lanienten equation to describe the interior of the star, can I use this to start the interior of the star? To start the interior of the
Yeah,
star?
there is a. I mean, we don't know actually why these stars show this. This is an open question. There is thing that is related with the fast rotator
So the
quality,
the peculiarity
but
is
it's
this.
not. They're peculiar. Yeah, they're not a normal B star. I mean, if you see the spectra, you can see well at least this emission line. But
Fast rotation is
Yeah.
obligatory
Okay.
to have such type of
So
spectra.
fast rotator.
Yeah,
Yes, it's necessary but not sufficient.
Yeah.
The fast
Yeah.
rotators, which nevertheless
Yeah, yeah.
fail to produce the disk.
perhaps some non-radial pulsations are necessary also to get the disks around fast rotating stars. And perhaps the dissipation and birth of new dissipation of these disks and the birth of new disks again is connected with these periods or epochs of many modes of non-radial pulsations when they either go in phase to support the formation of the disk, either to disturb each other, not to support the formation of the disk. So perhaps, but this is not sure yet.
Is the environment important?
Sorry?
So the environment of the star is important for creating this?
Environment? No, just inside. The
Okay, just
process
inside.
inside the star, yeah. Rotation and pulsations.
yeah, because it is material from the star. It's not an accretion disk. It's a regression disk.
Decretion.
Decretion is.
Yes, star. I was thinking of beryllium star. So this is to give you an idea of
Yeah. Okay.
my level of understanding of the stars. Yeah. Thank you.
Two very basic questions. What is optically thin and optically thick? envelopes?
It is
Like,
more transparent or not.
what is
as
the value at
transparent.
which you divide these?
No, there's not an exact value. It depends.
Because you are grouping them these in.
Yeah, because there was like an optically thin limit and an optically thick limit, but it's related. For example, in the optically thin, you use some line flux radio that came from another approximation that is from optically thin gaseous gas. And in the optically thick, you made another approximation, so you have values for the flux radio on these two extreme situations, and you have the VE stars, like in the VE stars and also V bracket and LBB is like all in this, in the Lorentz diagram, like in a diagonal joining these two extreme situations. So you say that if it's more close to the optically thick,
But if it has a very simple thing, like how much flux can be passed through this material? So say, how much for optically thick envelopes, how much flux, how much flux can be passed, say 70% or 30%, something like that.
yeah, I'm not sure how much, because it depends on how deep you can see the envelope in each line. It's not as much as flux passing the.
Pictorially explaining, when medium is optically thin, then as a rule, every photon created flies through the medium, not absorbed, will not be absorbed. And optically thick medium, for every photon created or emitted, there is a possibility, or how to say that?
Cross-section.
Expected path?
Optical depth is higher than 1 for the photon created to be absorbed. So this possibility of absorption is more than 67%.
One more question. Why does the equivalent width it increases with wavelength?
What?
The EW,
Yes, the equivalent width.
it increases with wavelength.
The lines are more intense.
If you show the EW graph. This one.
This one, yes.
So with increasing wavelengths, 4 micrometers.
Yeah, it is like
higher.
the dots are different lines that I showed you before.
So
it's not well.
why does it increase?
There is increasing the emission in the lines that we observe. We are observing bracket alpha is forming another region, so we are looking like a bigger emission surface.
Be related to rotation, right? Because equivalent width, if it is increases, as I understand it, it's because of the rotation of some region. Like this,
Yes,
this line,
but we are here. We have a star that is rotating with this velocity. This is the rotational velocity of the star in the equation. in the equator, and then the disk is following a Keplerian rotation, that is, the rotations drops with the square of the radius, the inverse of the square of the radius. So this is the rotational widening that you can see in the star, but it's not related to this equivalent width increase. I mean, if you observe one line that came from a part of the disk that is rotating at certain speed, and you see the same line in another disk with a different rotational velocity, yes, there will be a difference in this line, but that's not the case because we are working with one central star, and the disk is always Keplerian. So that is actually related with how many mass there is in the part of the disk that is emitting this line, because we are changing the density distribution. So if we, I can. So we start with a central density and we change this M value, lower, for example, this can be M4 and M2. So the density is different for each M. So if you're observing like this part of the disk, if you're observing this, you have a certain amount of mass. And if you're observing this, you have another amount of mass. And we are also changing this point, so we can observe that more bigger, higher density in the base of the disk, and we can also change.
So you're changing this density profile.
Yes, that we are changing.
But
the central density and how fast the density falls in the disk.
how does it relate to wavelength? I mean, equivalent width and wavelength. Equivalent width, I can picturize or imagine because of this differential rotation. You have this different rotation, so you can get different equivalent widths. But how does it relate to particular wavelength?
To each line, you say?
Yes.
Because, for example, if we are observing bracket alpha,
Each line, I don't know each line or not, because there was this graph of wavelengths, I mean 1, 2, 3, 4 micrometers. I mean the same part that we had. Yes, so 2,
Yeah.
3, 4 micrometers.
yeah, because this is bracket alpha, bracket beta, bracket gamma, bracket delta, bracket 9, 10, and all the lines
Okay,
that are
okay, so at different lengths, sorry.
here. This is bracket alpha. This is just the bracket series. If we see the spectra, in the middle there are another lines that we are not modeling yet. Here is bracket alpha, bracket gamma should be like in the middle of these two plots, but we don't have observation on this on this range. Bracket gamma, delta, and all the other lines of this bracket series. And we are modeling 9, 10, 11, 12 up to this line.
Okay.
That's
So why the width of these lines increasing if you increase the wavelength?
because we are looking at bigger part of the disk. I mean, each line is forming a different part of the disk. So if we are looking at the higher orders, we are looking in the most deep part, more close to the stars.
Okay.
I convince you.
So it's the more width. So from the deeper parts, I mean, where the density is very high, the central part, say 4 micrometer line is coming, particularly
It's
like that.
more,
And
it's
if you
more,
go
it's
away from.
a larger part of the envelope that we are seeing, if you are seeing the 4 millimeter line, that if you are seeing the 2 millimeter.
Yes, but it doesn't matter large part or low part, but it's the speed, rotation speed, which is giving this width, narrow width or larger width.
Yeah, but actually, if you're looking another part, it rotates slow.
Yeah, that's why you have this narrow.
Yeah. More than now.
Equivalent width, it decreases. Okay, now I. Thank you. Sorry, I had.
No, it's okay.
I also wanted to ask something.
Yeah.
You mentioned that you want to model or observe other types of stars. What do you mean by other types?
Not just V2, because we are using a V2 spectral type.
Okay. So anyway, B type stars, right?
Yeah, probably between late O and early A, that it's the spectral types that we have. If you see here that we have, well, this is just the more early, but we start with the 07, and the late one that we have is an A0.
Okay. So staying in this BE type general.
Yeah, sure.
Sure. And another thing I wanted to ask about these MX puppies.
Yeah.
The spectral lines. It is possible to see that there are wider wings of the lines.
It can be related with the inclination, because if you increase the inclination, then the lines is more wide. So it can be related with.
So these wings, wider wings, could come from different inclination.
Yeah, that's one possibility. Yeah.
Okay. Thank you.
And you have to include back to the model, like different.
Yes, but we model just following a few steps, and this is like in the middle. So it's like, it was just a first approach, but yes, the idea is to, once we have somehow a grid, started with this, and then like obtain the value from the inclination and for the density using the
Also,
more general view. If it is closer to this density, it's closer to this exponent, and well, a density close to the density that was previously found.
Also, okay, you said that about the width of the lines, that it could come from the inclination, but bracket lines from 10 to 12, they all nicely fit with the green line. But for bracket gamma, it is much better fit for the yellow line. With the different parameters.
Yes, it is possible that we may need different parameters in different part of the disk, because bracket gamma is in a region closer to the star than H alpha, but is outside the region of the last lines of this series. So it is formed probably not in the exactly same region that bracket 10 to 12. So we may need a different density, because if the star start to expel material, it is expected that the M value increase because the density drops very, very fast. I mean, you start with a very high density near the density fall. And if you're seeing bracket gamma, you are in a part that it's outside the part that has been already affected with this emission of material. So yes, it is possible to need different parameters.
And this M value, is it related to the viscosity of the disk, or it is different parameter? As I remember, the viscosity of the disk was one of the important ingredients in the HDUST.
The HDUST code use the VTT model.
Sorry?
The HDUST code use the viscous degradation disk model follows that.
Yeah, but you can change the viscosity.
No, I think that you don't. You can't. Not at least in this code.
Okay, because I was thinking that if you can change the viscosity, then it could create a different density profile and velocity profile in the disk. But okay.
Yeah, no, but it's VTT and Keplerian.
Okay. So now you know how to run it.
Yes. And how long it takes, because it's a few hours for each model.
Well, it's anyway, it is better than the exercise I had to do yesterday when I uploaded an observed spectrum to the web page, which is supposed to give me the best velocity model. And I'm waiting already for the second day for the result. So okay. Thanks for very interesting presentation. It was very interesting for me to follow.
Thank you.
No more questions, then thank you again.